So our goal now is going to be to construct a number system. So we want to construct the natural numbers, also known as the counting numbers. So like 1, 2, 3, etc. And actually we'll start with 0. And starting with 0 ends up just being more friendly in terms of the way that we're going to do it. So 0, 1, 2, 3, etc. So we want to construct this system. And I'm going to start with this question. The reason I'm starting with this is that it turns out not to really matter exactly how we define what the number 1 or what the number 2 is. What turns out to really matter is what it does. If something acts like 1 or acts like 2 when you do things with it, like look at ordering, is 1 less than 2, is 2 less than 1, or look at arithmetic, like what is 1 plus 1? If things act like the numbers that they're supposed to act like, then they are those numbers pretty much. Still though, we need to give them definitions. So we need to find somebody in the mathematical world that we've kind of created and give that somebody the name 0. And we need to find somebody and give them the name 1. And we need to find somebody and give them the name 2. So who's it going to be? We could bring in some axioms and create some new characters, or we could find things that are already there in the world. You can, as you might guess, it's better to not create new axioms unnecessarily. If we can fold in the thing that we're trying to build up into the system that we already have, then that's definitely a better option. So this is why I'm starting with this question. What things are there in the world that we have created? Is there somebody that we can find and give the name 0 to? Is there somebody that we can find and give the name 1 to? Well, there are not really that many things that we've been talking about so far. Okay, so what do we mean by things in the world? So by things, I mean something that you can refer to by writing a mathematical term. So we can rephrase the question like this. What specific things are we able to refer to by writing down a grammatically correct mathematical term? So mathematical terms will refer to mathematical things in the same way that in English, nouns or noun phrases can refer to physical things or abstract ideas or whatever. So the thing by things in the world, things in the mathematical world, I mean things that you can refer to. So one thing you might think of is, what about x? If I just say x, that is a variable, and so it's a term. And so it refers to something, right? But it doesn't refer to a specific thing, right? It's kind of like a pronoun in the English language, like he or she or they. These do refer to things, but you need a particular context to get them to refer to any particular thing, right? So those don't count as ways of referring to, those don't count as particular things, right? In one context or another, they might refer to particular things, but just uttering these words by themselves doesn't give you the ability to refer to any particular thing. So same problem with x. Depends on the context what it's actually referring to. Now, the things that we are able to refer to, we have to refer to using mathematical language, right? So you can't say that, for example, me, the physical me that's sitting here, that's not something in the mathematical world, right? There's no term that I can write down that refers to that refers to me, or that refers to you. But what can you find that refers to any particular thing? So if you want, you can pause the video and see if you can think of some way to write down a term that refers to a specific thing. And if you did that, I'm assuming maybe you did that now if you wanted to, here is something. The empty set. That's a specific thing in the mathematical world. And we can write down this is a constant, this symbol is a constant, so that refers to that thing, the empty set. What else is there that we can refer to? Is it only the empty set? Maybe we've created a world inhabited by one thing, which is this. Can you think of something that isn't equal to the empty set? So you might say, a set consisting of x. But if you just say that, that's not really any specific thing, because again, it depends on the context what the variable x is. So can you think of something that isn't the empty set? Are there any other characters in our universe? Here's what you might come up with. This thing. A set, the empty set, but packaged in another pair of brackets. So this one is definitely not the same as this one, because, for example, this one is empty and this one isn't. This was actually an exercise earlier. Exercise 40 was proving that these two things are not equal. So here are two specific characters in the mathematical universe that we've made here who are different. And here's another one who's different. So there are at least three different, and it's pretty easy to convince yourself that this is different from this. So there are at least three characters. So here's one, and here's another one. These are all different things. So we could just slap a label 0 on this one and be like, okay, whenever I write 0, that's just a shorter way of writing this. Whenever I write 1, let's make that just a shorter way of writing this. Whenever I write 2, we'll make that a shorter way of writing this. And so on. And so now I've finally got somebody who's named 0, somebody who's named 1, somebody who's named 2. And maybe somehow I can figure out how to get infinitely many things there. Definitely I can't write down infinitely many labels or create infinitely many individual, like atomic labels like this, since I only have finite ink and paper or finite time in which to introduce new rules. But somehow I might be able to make that work. And what makes these then be 0, 1, or 2? It's going to be the way they interact with each other, right? So like, if you want it to be true that 1 plus 1 equals 2, then you have to define plus in such a way that when you add this thing to itself, you get this thing, right? So it's all about how they interact with each other. It doesn't really matter who they are on the inside. Okay, well, we're not quite going to do things this way, although this is a way to do things. Some people do things this way. We're going to do things a little bit differently. And in the way we do things, actually 0 is going to be this. 1 is going to be this, but 2 will not be this. 2 will end up being something else, sort of similar and sort of related. The way we're going to do things is going to give us a nice way of using the set theory stuff that we've already created to talk about how the natural numbers are ordered. So if we did it this way, then it would be difficult to explain what we mean when we say 0 is less than 1 and 1 is less than 2, and so 0 is less than 2. It would be difficult to express those things in set theoretic language, although possible. So we're going to do things in a different way. It still starts out like this, but the pattern continues differently, and it ends up being a much more set theory friendly way of setting up the ordering. All right, so you'll see how that works. Right now, with a new notation that we are introducing. So here's the syntax for this new notation. Take any term, so any object that you already can refer to, write down the expression that refers to that object, and then if you wrap it in the word next with some parentheses like this, then the result will be another term. So this is a term. And that's it for the grammar. So this is a way of building terms from terms. And it's not a function. So just because I'm writing this with the parentheses, this kind of notation that looks like evaluation, that doesn't mean I'm creating a function. So it's not like next means anything on its own, right? I can't just write next by itself. It's a lot like when we introduced power sets, we just said, like, if you take a term and then you wrap it in this symbol, fancy P with some parentheses, then that creates a new term, and here's how we define it. It's not like p by itself would mean anything. If you just wrote this symbol, fancy p by itself, that would not be any kind of function. It would be meaningless. It's just that this notation as a whole is being given this meaning. It's a definition, so it's actually unnecessary in the language. Technically, it's not necessary, because instead of writing this, you could just write this out every time, right? The definition is just providing a shorter way to write things. So this is going to provide a shorter way to write something. What is that something? It's the following. So when we write next of something, that's a short way of writing that something union singleton that something. And this is definition 89. So you could just totally do away with this definition and instead, if you want, just write this every time. All it's doing is providing us with a short way of writing this. Actually, it's not really any shorter, right? Here you have to write, it's even longer actually, right? This is like 4 words, 4 letters, right? Whereas here, you only need to introduce this symbol, and this symbol. Okay, anyway, it's still more convenient because it's going to help communicate intention. And what is the intention? Is that when we write next x, this is supposed to be, and you cannot use this idea to prove anything, but this is just what it's intended to be. It's supposed to be the number after x, just the next number. It's the next of x. Sometimes it's called the successor of x. So if you, in computer science language, if you increment x by 1, what's the next thing that it would be? If you want to write this in LaTeX, just the same way you did domain and range, you can do text next, in curly braces. Something like that. This would work. And here's our next definition. 0, so these are 10 constants that we're defining. So 10 new constants are getting introduced into the language. 0 is going to be just another name for our good friend, the empty set. So we totally did not need this symbol in our language. It's a definition. None of it was needed, right? This is all just a convenience. So instead of writing empty set, we might sometimes write 0, and that will mean the same thing. It will help to communicate our intention when we use the symbol 0 rather than the symbol the empty set. Whenever we write the symbol 1, we actually just mean this. Whenever we write the symbol 2, we mean this. Okay, so this is 10 new constants that we have introduced. We can introduce more if we want to. We definitely have a way of referring to what you might call 10. You can just refer to it as next 9. We haven't introduced a symbol for it, but you could just write next 9 if you wanted to. And then what you might call 11 is next 9, and so on. But to be honest, we're actually not going to use this very much. It's mainly just going to make an appearance in some exercises where you use small numbers for examples for certain things. But for setting up general theorems and exploring what we're about to build, the collection of all natural numbers, these are not going to be too useful. Okay, so we did actually go and find a character in our universe, the empty set, and we slapped the label 0 on it. And then if you look at the way this works, 1 is the next of 0, right? So 1 is the next of 0, meaning it's the next of the empty set. And the next of something is that thing unioned with the singleton of itself, right? And what's the empty set union singleton the empty set? Well, the empty set acts as an identity for union. If you union anything with the empty set, you just get that thing, right? So it's not really going to affect anything to union with the empty set, so you just end up with this. And that's what I've written here. So indeed, we have gone and found this character, and we have slapped the label 1 onto it. Now, what's 2? It's not going to be just tacking on another pair of curly braces, but I'd like you to play with the definitions and in the quiz figure out what curly braces arrangement 2 ends up being. So I'll leave a question mark there for you to play with the definitions. So these things that you can get by starting with 0, starting with the empty set, and then nexting your way up, next, next, next each time, these are called natural numbers. But what we'd like to do is construct the set of all natural numbers. And definitely we don't have infinite time to keep writing these definitions. So there's no way we can sit here and just keep writing next to construct formally the set of all natural numbers. So how can we do this? So here's my question. How can we define the set of all natural numbers? This is our first real dive into something infinite. Until now, we have had singleton as a way of building sets that contain one thing, and then we've had doubleton, we've had these other ones, ways of listing elements, and they're just these chains of OR. And that works great for defining what you might call finite sets. We haven't defined that term, finite, but you can imagine that these are finite sets. This is not the only way we have of defining sets. Of course, there's the tool that we use to define these in the first place, which is this notation, the sort of collector notation where you write a variable and you put a bar, and then you write some membership condition. In other words, the notation that is powered by axiom 5. So this notation has always been available for doing things with infinite sets if we want to. If you want to define an infinite set, just make your membership condition be something that could possibly hold for an infinite collection of things. Well, what makes the particular infinite collection of things that we're now interested in, what makes that special? It's that it doesn't really seem like we're interested in membership condition. If you want to define the set of natural numbers, you need to say what it means to be a natural number. And that's quite a weird condition, right? So to be a natural number, it sounds like you have to either be 0 or you have to be obtainable from 0 by a chain of next. That's quite a difficult thing to express as a mathematical proposition, as the phi in the membership condition. So here's what I'm getting at as what might be the first way you try to define the so-called set of natural numbers. So this is an attempt. Is you might try to say it's the set of things that have this property, that either it is 0 or it is the next of the next of the next of, and so on, for some number of these nexts of 0. Something like that. That's what a natural number is. But this is not really a mathematical proposition, right? Dot dot dots are not part of our grammar, and we don't know how to prove anything if you write dot dot dots, right? That doesn't power any proofs. So this seems to be a real puzzle. How do we define the set of all natural numbers so that we can work with it? Well, we can try to do something kind of circular. How about, and this is still an attempt that's going to fail, but how about saying that a natural number is something that's either 0 or it's the next of a natural number. So maybe it's the next of some, let me use the same family of letters, maybe it's the next of some y for some y in there. Maybe something like that. It seems kind of circular because I'm using this symbol in my attempt to define that symbol, right? But it at least expresses what I'm trying to say, that it's the set of things that either are 0 or are the next of something in that very same set of things. Now, this is, okay, so because it's circular, it should feel quite unsatisfying. But there's also a problem, which is that this is no longer a definition if we arrange things like this. It's more of a statement of a property, right? It's more like we're saying that whatever n is, it has this property. Since n shows up on both sides of the equal sign here, you really can't say this is a definition, right? If I can put something on both sides of an equal sign, then I can definitely just start spouting contradictory things and call those definitions. And if you remember from our discussion about definitions, definitions are not supposed to really change the power of the axiomatic system that you're constructing. They should not let you prove more or fewer things. Importantly, they should not let you prove more things than you could before the definition. All they should do is provide shorter names for things that were already there, right? That's what a definition is. It's just like, take this long string of symbols, I'm just going to use this short thing to refer to that long thing. But if I just state this property about n and make that an axiom, then that truly is an axiom and not a definition. In other words, how do I know there is an n that has this property? Okay, so we reject this approach for the reasons just given. It's just not really a definition. It might be a fun thing to include in an axiomatic system, and I'm sure there are people who have tried this, and I think it can work with some success to just start with something like this as an axiom. But that's not what we want to do. We want to define n using the things we already have in place. Okay, so by now I've already got the syntax and the semantics in place, so let me just officially put that up. This symbol, the n like this, is a constant. So it's like a noun, a proper noun, kind of. It's just a symbol that refers to a specific thing. So suddenly we have gone from having, I think, one constant in our language, the empty set, to, at this point, we have several. We have the empty set. We introduced these 10 new constants here, and we also have n. Semantics. This is supposed to stand for the set of all natural numbers. So 0, next 0, next 0, etc. Of course, that's why this is just semantics. It's the intended meaning. Etc. is not a real mathematical term, so it cannot go here. LaTeX. Let me skip formalism for a second. In math mode, so when you're in between dollar signs or double dollar signs, you can do this. Math BB, and then just stick a regular capital N in there. What I would recommend is doing a new command to create a shortcut for it. So maybe somewhere up top you can do something like this, somewhere at the top of your document, and then from that point on you can just type \n while in math mode, so like this, to typeset it. So the font, when you're handwriting this, you just do 2 lines like that. The font is called Blackboard Bold, so that's what the BB is. All right, and finally for the formalism, I will put that all in the next video, but it's going to be these 3 things. Definition 91, definition 92, and theorem 93 coming up right here. So we're going to define first what it means for a set to be inductive. Then, finally, in definition 92, we're going to define n essentially to be the smallest possible inductive set. And you'll see what that means in the next video. And then we will prove theorem 93, which will essentially be establishing that n has the properties that we were trying to give it over here. So basically, we will prove that it has these properties after defining it using the language that we do have available to us. And we're going to define it in a way that is not circular. All right, so next video, these guys.